When news broke from Geneva, Switzerland, that Albert Einstein might have been wrong for decades, the scientific world was sent into a frenzy. Einstein, the iconic physicist who reshaped our understanding of the universe, had long insisted that the cosmos obeyed strict rules of locality. But what if he was wrong? Quantum computers have now delivered undeniable proof that Einstein's classical worldview doesn't hold up. The implications are staggering, and reality, as we know it, just got a whole lot weirder. Buckle up. We're diving deep into the quantum realm to explore how Einstein's assumptions have been shattered and what this means for our understanding of time, causality, and the very fabric of existence. In the classical realm of physics, time is often regarded as an absolute frame of reference. This perspective, heavily influenced by Newtonian physics, echoes the simplicity of our daily experiences. Sir Isaac Newton described time as absolute, true, and mathematical, flowing uniformly regardless of external conditions. Under this paradigm, events are neatly ordered along a timeline where cause precedes effect, and each moment is fixed once it has passed. Consider a swinging pendulum or a falling apple. The behavior of these objects can be precisely predicted using mathematical equations, and their future states can be determined with remarkable accuracy. In such a universe, the idea of altering the past is not only unfathomable, but also logically prohibited. Sending a message backward in time or changing a previous outcome contradicts the well-established concept of causality, where every effect stems from a preceding cause. This classical understanding is deeply embedded in the way we structure our world. Thermodynamics, for instance, reinforces the concept of the arrow of time through the second law, which states that entropy, or disorder, tends to increase over time. This marks a clear direction from order to disorder, cementing the idea that history is immutable. The past is fixed, and the future remains open, but only in the forward direction. Despite these elegant formulations, the assumptions of classical physics begin to crumble when we turn our attention to phenomena at the subatomic level. As we'll see, the universe at the quantum scale does not adhere strictly to these time-honored rules. The next part of our discussion moves us from the seemingly secure territory of classical thought into the realm where uncertainty and strange correlations reign supreme. The birth of quantum mechanics and the uncertainty principle. At the dawn of the 20th century, scientists faced puzzles that classical physics could not explain. Experiments in areas like black body radiation and the photoelectric effect hinted at underlying processes that defied conventional wisdom. This marked the beginning of quantum mechanics, a revolutionary framework that redefined our understanding of nature at the smallest scales. Central to quantum mechanics is the notion that particles are not confined to definite states prior to measurement. Instead, they are described by a wave function, a mathematical representation that conveys a spectrum of probable outcomes. In this context, what we might consider an electron's position or momentum is not fixed until an observation is made. The famous uncertainty principle, introduced by Werner Heisenberg, quantifies this very idea. The more precisely one property, like position, is known, the less precisely another, like momentum, can be determined. The early pioneers of quantum mechanics, Max Planck, Niels Bohr, and Albert Einstein, among others, paved the way for a radical shift in scientific thought. Planck's hypothesis that energy is quantized broke down the notion of continuous energy change, while Einstein's work on the photoelectric effect demonstrated that light itself can exhibit both wave-like and particle-like characteristics. These early triumphs laid the groundwork for a theory that would not just describe, but also fundamentally challenge our conceptualizations of reality. Within this emergent framework, the physical world was seen as a playground where probabilities simultaneously represented multiple possible futures until they collapsed into a single outcome upon interaction with measurement devices. The idea that observation itself could shape the reality of a system raised questions far beyond traditional mechanics. a concept that extends naturally into the study of time and causality. Quantum entanglement, the cosmic link. Perhaps the most captivating discovery in quantum mechanics is the phenomenon of quantum entanglement. When particles interact under certain conditions, they can become entangled, meaning their fates are intertwined in a way that defies classical explanation. In such cases, the state of one particle cannot be fully described without making reference to its partner, no matter how far apart they may be located. Imagine two photons created from a single event. Their physical properties, such as polarization or spin, become correlated to such an extent that a measurement on one instantly reveals information about the other. For instance, if one photon is observed to have a vertical polarization, its entangled partner will exhibit the corresponding complementary trait, such as horizontal polarization. This instantaneous correlation occurs despite the spatial distance between the particles. This idea challenges the conventional wisdom that suggests information must travel at a finite speed, no faster than light, to make its way from one location to another. Instead, entanglement indicates that the quantum world is woven together by a fabric of interconnections that transcends the classical limitations of time and space. Measurements performed on entangled particles have produced results that appear to be non-local, meaning that the outcome of detecting one particle is correlated with the outcome of its distant partner, regardless of the separation. This observation led to a significant philosophical conundrum in physics and sparked debates about the completeness of the quantum description of reality. The seemingly instantaneous coordination between entangled particles forces us to consider that the universe might be far more interconnected than our everyday perceptions would have us believe. Even though entanglement does not by itself allow for practical backward communication or time travel, it introduces the idea that the boundaries of cause and effect are not as rigid as once thought. Exploring Bell's theorem. To test the predictions made by quantum theory regarding entanglement, physicist John Stuart Bell introduced a set of inequalities that would later come to be known as Bell's inequalities. Bell's theorem provides a quantitative way to compare the predictions of quantum mechanics with those of classical theories based on local hidden variables. In simpler terms, local hidden variable theory suggests that particles carry pre-established answers for every possible measurement, thereby eliminating any need for spooky interconnections. Bell proposed that if particles truly behaved as completely independent objects with pre-assigned values, then measurements taken along various orientations should satisfy certain logical ratios or statistical limits. However, if the predictions of quantum mechanics were valid, the observed results would violate these predetermined limits. Over time, numerous experiments were designed to test Bell's inequalities. A landmark series of experiments conducted by Alain Aspect and his colleagues in the 1980s, and later refined by others, demonstrated violations of Bell's inequalities. These experimental results confirmed that the correlations seen between entangled particles were stronger than what any classical or local theory could account for. Consequently, the idea that particles can contain hidden instructions that govern their behavior was largely set aside in favor of the counterintuitive predictions of quantum mechanics. Through these pioneering experiments, it became evident that the physical world, at least at the quantum scale, operates under rules fundamentally different from everyday experience. The data show that once a measurement is made on one part of an entangled system, the corresponding property of the partner particle is determined in a manner that does not adhere to classical local realism. This realization not only bolstered the quantum description, but also opened up a realm of inquiry where the nature of reality is perceived through the lens of probabilistic outcomes and instantaneous connections across vast distances. Bell's work thus acts as a bridge between theoretical musings and experimental verification in quantum physics. The rigorous tests stemming from his theorem have reshaped the philosophy underpinning our understanding of time, causality, and the very fabric of the universe, inviting further exploration into how these effects might intertwine with other anomalies in the quantum domain. The intrinsic properties of particles in the quantum world. In the quantum world, spin is not an indication of literal rotation, but rather an intrinsic property that determines how particles interact with magnetic fields. Quantum spin can manifest in discrete orientations, usually designated as up or down relative to a chosen axis. This discrete nature, a stark contrast to classical angular momentum, provides a neat example of how particles exhibit behavior that is inherently probabilistic until measured. Consider a pair of entangled particles with their combined spin set to a conserved value, often 0. When the spin of one particle is measured along a specific direction, the measurement not only forces that particle into one of the allowed states, but also instantaneously fixes the corresponding state of its partner. If one particle is measured as up, then the other must be down to conserve the overall spin value. Before measurement, each particle exists in a superposition of both spin states. It is only the act of measurement that forces the wave function describing these particles to collapse into a single outcome. This process means that the particles do not possess a definite value for spin until they are observed, fundamentally altering our perception of what it means for an object to have a property at a given moment. The study of quantum spin has significant repercussions, prompting us to question the nature of predetermined properties in subatomic systems. In experiments where detectors are oriented in various directions, the statistical distribution of spin outcomes has been shown to deviate from classical expectations. The probabilities adhere strictly to the quantum mechanical predictions rather than any pre-assigned instructions. Such experiments underscore that the intrinsic properties of particles are not fixed until interacting with a measurement apparatus, thereby reinforcing the central role of observation in shaping physical reality. These insights into spin and measurement bring forward the notion that, at the quantum level, the fabric of reality is not carved in stone, but is instead a dynamic interplay of potentials, where even the most fundamental characteristics remain in a state of flux until determined by interaction. The delayed choice experiment. One of the most striking experiments probing the connection between observation and history is the delayed choice experiment. Building upon the famous double-slit experiment, this variation challenges the conventional notion that a particle's behavior is determined at the moment it traverses its path. Instead, the experiment suggests that the decision made after the particle has passed through a critical juncture can seemingly affect how it behaved earlier. In the classic double-slit setup, particles such as photons are sent through two closely spaced openings. When no measurement is made to determine which slit the photon passes through, the light creates an interference pattern on a detection screen, a signature of wave-like behavior. Conversely, if a detection mechanism is implemented to observe which slit the photon used, the interference pattern collapses, and the light behaves like discrete particles. The delayed choice experiment introduces a twist by postponing the decision to measure the particle's path until after it has already passed the slits. A common experimental design involves sending a single photon to a beam splitter that divides its path into two possibilities. Further along each path, mirrors direct the photon to converge at a point where a second beam splitter can be optionally inserted. Crucially, the decision to introduce the second beam splitter is made only after the photon has departed from its initial splitting stage. The experimental outcomes are astonishing. When the beam splitter is inserted at the later stage, interference is observed, implying that the photon had traversed both paths simultaneously, even though the decision to cause interference was made after the photon had been en route. If the beam splitter is removed, the interference vanishes, and the photon behaves as if it had traveled only one path. In essence, the particle's prior behavior appears to be determined by a measurement decision that is taken in hindsight. This experiment compels us to rethink the role of time in quantum mechanics. The observation, which in classical terms should only affect events in the future, seems instead to have an impact that reaches backward. Despite this seemingly paradoxical outcome, no practical contradiction arises. Rather, the behavior is fully consistent with the mathematical formalism of quantum theory. The delayed choice experiment thus shifts our conversation from classical location and timing to a domain where time and measurement become deeply interwoven. Building on the ideas of delayed measurements, quantum eraser experiments further probe the nature of information and observation in quantum systems. In these setups, information about a particle's path, collected in an initial measurement, is later erased, leading to the reappearance of interference effects that had previously been suppressed. In a typical quantum eraser experiment, entangled particles are generated and directed along different pathways. One particle, often called the signal, passes through an apparatus that could potentially reveal which path information. Its entangled companion, the idler, is sent to a separate detection scheme where experimentalists have the option to manipulate whether the which path information remains accessible or is effectively erased. When the which path information is preserved, the interference pattern usually associated with wave-like behavior does not manifest. However, if the information is deliberately erased through additional quantum operations, the interference pattern is restored, as if the particles had never been forced to choose between multiple paths. What is especially intriguing is that the decision to erase the which path information can be made after the signal particle has been detected. The recovery of the interference pattern, even under such conditions, underscores the counterintuitive role of measurement in quantum mechanics. The data's ultimate form depends not only on the initial conditions, but also on the subsequent manipulation of the system. These experiments demonstrate that the act of observation is not a passive recording of an objective reality, but an active component in dictating which aspects of a quantum system become manifest. They reveal that the removal or retention of information is a process that can directly influence experimental outcomes, challenging our standard notions of temporal causality. In effect, quantum eraser techniques illustrate that the boundary between past and present becomes porous in the quantum domain, as operations performed after an event can modify the observable features of that event. The possibility of information. Reversing time flow. Beyond the immediate peculiarities of measurement, the experiments discussed so far invite speculation about retrocausality, a scenario in which future events influence preceding ones. At first glance, retrocausality appears to conflict with our conventional ideas about cause and effect. Yet, in the quantum framework, it emerges as a viable interpretation to account for experimental results that defy classical intuition. Retrocausality posits that, under certain quantum circumstances, the act of observation or measurement can travel backward to affect the state of a particle before the measurement takes place. This notion is not meant to suggest that macroscopic objects can be rewound like a videotape, nor that one might send a detailed message to one's own past. Instead, it is an explanation for why certain experimental outcomes, such as those seen in delayed choice and quantum eraser setups, appear to display an influence of future conditions on initial states. In this interpretive framework, the conventional flow of time is not strictly unilateral. Instead, there is an underlying symmetry between cause and effect, where both past events and future measurements are mutually entangled in a dynamic process. Although retrocausality remains a topic of lively debate within the physics community, several theoretical models and interpretations have been proposed to reconcile experimental observations with the possibilities of backward information influence. These models do not allow for paradox in the traditional sense. Rather, they paint a picture of an inherently non-classical world where time is woven into a network of probabilities and correlations. The concept of retrocausality encourages researchers to examine the foundational assumptions of time ordering in nature. It raises questions about whether our classical notion of an irreversible timeline adequately captures the complex interdependencies observed at the quantum scale. While practical methods to harness retrocausal influences for information transmission remain in the realm of thought experiments, the possibility itself continues to be a fertile ground for both theoretical exploration and experimental ingenuity. From laboratory discoveries to the world of interactive media, the counterintuitive insights emerging from quantum mechanics do not exist solely in academic papers and high-precision laboratories. Over time, these ideas have seeped into popular culture, influencing a wide range of creative expressions, from literature to cinema, and even into the realm of video games. The imaginative application of quantum phenomena offers artists and designers an enriching palette on which to base their narratives, crafting stories that resonate with the mysteries of the subatomic world. In the sphere of interactive media, video games have proven particularly adept at translating complex scientific ideas into engaging experiences. Developers are drawn to themes of uncertainty, time loops, and parallel outcomes because they offer fresh mechanisms for interactive storytelling and gameplay innovation. The interplay between player choice and evolving storylines, where actions in one moment might have rippling effects later, or even seem to redefine earlier events, mirrors the quantum concept that outcomes are not decided until they are observed. Within this creative context, the influence of quantum mechanics becomes tangible. Rather than merely presenting abstract theories, games imbued with these ideas encourage players to participate in a dynamic exploration of causality and consequence. This fusion of science and art not only brings a level of intellectual engagement to the medium, but also invites audiences to reimagine the boundaries of what is possible in both narrative and design. Futuristic quantum technologies. The insights gleaned from experiments in quantum mechanics have seeded the development of transformative technologies that once seemed purely speculative. Quantum computing, for instance, leverages the principles of superposition and entanglement to perform calculations far beyond the capabilities of classical computers. By encoding information in quantum bits qubits, which can exist in multiple states simultaneously, these computers promise dramatic leaps in processing power and efficiency. Beyond computing, quantum communication represents another frontier where theory and application converge. Quantum key distribution, QKD, utilizes the inherent unpredictability and entanglement of particles to create communication channels that are virtually immune to eavesdropping. In practice, any attempt to intercept or measure the quantum state of transmitted information immediately disrupts it, alerting the communicating party to potential security breaches. Practical implementations of these technologies are already under development, with the vision that they will one day revolutionize secure communication on a global scale. Researchers are also exploring ideas related to quantum teleportation, not in the science fiction sense of transporting matter instantaneously, but as a means of transferring information between distant points. This process involves the quantum states of particles, enabling the recreation of a state elsewhere without physically moving the particle itself. While practical applications remain challenging, progress in these domains continues to push the boundaries of what might one day bridge the gap between theoretical possibility and technological reality. Emerging technologies anchored in quantum principles often blur the lines between science fiction and science fact. The rapid advancements in these fields demonstrate that many concepts once relegated to the realm of speculative fiction are beginning to find concrete realization. Within the scientific community, several emerging paradigms continue to challenge and expand our understanding of time at the quantum level. As experimental techniques become increasingly sophisticated, researchers are exploring new avenues of inquiry that straddle the domains of quantum mechanics, gravity, and cosmology.